This is the conversation with Scott Aaronson. He's a theoretical computer scientist, professor at the University of Texas, Austin, and one of the leading innovators in the fields of quantum computing and computation complexity. In this conversation, we discuss, can machines think? Is it enough if they can just behave as if they think? We also explore his journey into computer science. We talk about the fields of quantum computing, some of the myths associated with it. And then we talk about computation complexity theory, P, NP, the P versus NP problem, and AI and consciousness. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars in Apple Podcasts. This project takes a lot of my time, money, and effort. And now it's officially my full-time job. I've retired from a corporate job. So if you'd like to see this continue, please consider making a donation on Patreon or Anchor. You can buy Super Thanks on YouTube. You can join as a member on YouTube, or you can leave gifts on Instagram Reels. If not through monetary channels, and do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally.
And now, trust me, it is no time. It is no time. It is no time.
Alan Turing had published a paper in 1950 titled Computing Machinery and Intelligence, in which he asked the question, can machines think? And then very quickly, he dismissed that question as senseless, and he replaced it with the question, is it enough to say that if a machine can just behave as if it thinks, whether that's enough in itself? And his case for the motion is purely functionalist. He said that if machines can behave, then that is enough. If they can just imitate a thinking system, then that's enough. I want to get your take on this. Can machines think? If not now, then maybe ever in the future? And do you agree with Turing that it's enough to say that a machine, if it just behaves as if it can think, if it can just ace the imitation game, then that's enough, even if it's not actually capable of original thought?
Well, I think that Turing's point was to clearly separate the two questions, right? The first question is, can you build a machine that behaves indistinguishably from a human? The second question is, supposing you did, would that machine have inner experience as we consider ourselves to have? Would it be conscious? And so forth. The problem is that people constantly munge these two questions together. Right. So like they will say, well, a computer could never be conscious, but then as evidence for that, they will just give empirical criteria. Right. They'll say, well, for example, we never see a machine do this, right, or do that, fall in love or write a poem. Right. And so they constantly set themselves up for empirical refutation, right? Like it's like they don't even take it to the very next step of, okay, well, suppose that a machine does do that thing. Then what? Right? What happens to your argument then, right? And, when we've seen that in practice, what happens is that just without blinking, they move to the next thing that they say that a machine will self-evidently never do, right? So this is just like hopelessly confused thinking, right? And so I strongly support, Turing's project of just clearly separating the two questions, the empirical question and then the metaphysical question, right? They are different. Right. So we get to define words to mean what we want them to mean. Right. There is no true answer to what thinking means. Right. But, if you cash it out to mean something that is empirical, right? Something that, is not about your inner experience, but about behavior, what games you can play, what kinds of conversations you can have, then I think, we don't know anything in the laws of physics that would prevent a machine from doing everything that we do. And we could say something stronger than that from a certain point of view, if you believe in reductionism in chemistry and physics, then ultimately we are also machines. We are machines built out of carbon instead of silicon. But we are also made of atoms that obey, clear laws, the laws of quantum field theory and so forth. And so, if you knew enough about the state of all of those atoms, then you could put all of that onto a computer. And then, that computer, by hypothesis would behave indistinguishably from us, right? A next question that you could ask is, well, would there be anything that it would be like to be that computer? Right. But I think people need to be clear that this is a type of question that goes back to like the very beginnings of philosophy. Democritus was asking this sort of question in 400 BC, right? And it's not obvious if we've really made any progress on this kind of question in all those millennia, or what progress on those questions would even look like, right? I mean, how do I know that you are conscious, that you're not, some automaton, right? How do you know that I'm conscious? Right, and you get to like all of the usual, sort of a late night sophomore type of questions, right? How do I know that your red is the same as my red? Your blue is the same as my blue. Maybe, when we look at these Legos, it's our subjective experience is switched, even though all the external behavior is identical. Okay,
This is the hard problem.
These are the hard problems of consciousness, and so you can continue to wonder about those, even in a world where AI can do everything that we can do. But it's also extremely important to say that, when like sometimes people will say, well, I don't believe that an AI could be conscious in the way that humans are, and therefore I'm not worried about these, AI existential risk scenarios, or AI taking over the world. That's a complete non sequitur. Right. That's just, again, it's once again showing the danger of confusing these two different realms. Right. Even if AI, was not conscious in the way that we are, which, you could say, how would we ever know? Right. That still would not prevent it in any obvious way from, doing all of the observable tasks that we do, passing all the same tests, coming up with, scientific insights, writing articles, and possibly, endangering us, taking over the world, rendering us extinct, right? So, you can worry about all of those things, even if, you believe that consciousness for some reason is limited to carbon-based biological life and can't be replicated in silicon. That's just a separate question.
A lot of things to explore here.
Yeah.
I'm going to park the question about consciousness aside because I do want to revisit it after we've spoken about complexity. But you did bring up reductionism, so let's go there first. In your essay, The Ghost in the Quantum Turing Machine, you said that I idealized Turing as an uber reductionist, the scientist who had gone further than anyone before him to reveal the mechanistic nature of reality. Through his discovery of computational universality, as well as the Turing test criterion of intelligence, Turing had finally unmasked the pretensions of anyone who claimed there was anything more to mind, brain, or the physical world than the unfolding of an immense computation. After Turing, it seemed to me one could assert with confidence that all our hopes, fears, sensations, and choices were just evanescent patterns in some sort of cellular automaton. That is a huge array of bits, different in detail, but not in essence from Conway's famous game of life, getting updated in time by simple, local, mechanistic rules. Consider this your annual status update, status check, but do you still believe whether the universe can be reduced into small bits and simple lines of code and rules? This is something John Wheeler called it from bit. Do you think simple computation is the source of all this complexity in the world?
Yeah, so what you left off about that essay was that I then went on to point out that Turing in the last months of his life sent these postcards to his friend saying the universe is the interior of the light cone of creation. Science is a differential equation. Religion is a boundary condition.
Yeah.
Right? So he was clearly exploring, if there was something more than this, right? If reality were more than just the unfolding of a computation, how would that work, right? And he was actually, it seems, gravitating toward the same sort of answer that I would if you ask me that question, which is, well, we have in physics these extremely detailed theories now that say once you specify the state of a physical system, right, then how does that state evolve in time? How does it change, right? And this was, in some sense, this was the whole program of physics from Galileo and Newton onwards, right? To express all physical phenomena in terms of, differential equations. And, some people think that quantum mechanics completely overturned that, right? But also in quantum mechanics, we have this wave function, right? We have this state that is supposed to encompass everything that is knowable about a physical system. And if you know the wave function, well, you can't predict with certainty what you're going to observe when you look at that system, but you can calculate the probabilities of all of the possible outcomes, right? So at least in that probabilistic sense, nature still seems like this completely mechanistic thing, okay? The one thing that physics doesn't do is give us a good theory of initial conditions, right? So it doesn't tell us, well, most obviously, why was there a Big Bang? Why was the entropy of the universe very small at the Big Bang, right? Which was sort of what set the stage for everything that followed, right? The increase of entropy that's associated with, all the complex phenomena that we see in the universe, right? And you could even wonder, if your goal was to predict the actions of a specific person. So, not to build an AI, let's say, but to know what this person is going to do, right? Then would you need to know, the exact state of all of the molecules in that person's brain? And is it even possible to know that without killing the person in the process, right? There are, one thing that quantum mechanics does tell us is that there are limits to how accurately you can measure the state of a system without disturbing the state. Okay, so you could say, maybe from a God's eye perspective, we are all automatons, right? We are all at least probabilistically predictable, by knowing our wave functions. But because we ourselves are embedded within the universe, we even in principle, we can have only limited knowledge of, and we may not even be able to predict the probabilities that people will take certain actions or other actions because we simply can't know their initial states. We can't know the states of their brains or of their environments to a high enough precision to make those predictions. Okay, and so that could actually give you some sense of, some notion of free will, which might be, unsatisfying to some people, but which might be the strongest notion of free will that the laws of physics can really support or back up. So my goal in that essay that you quoted from was really to explore that point of view. And you asked for a yearly status update. I would say, I remain uncertain about this. I mean, I feel like if there were something that went beyond, just, the universe as an unfolding computation, then, that's my best guess for what it is, something about the initial state, right? Because that's sort of the only thing that, physics does not, point toward a theory that sort of totally explains, right? I mean, we have, we don't have a complete theory of quantum gravity, right? But if gravity is going to be subsumed into quantum mechanics, as for example, the string theorists believe that it will be, so if we're going to have a quantum theory of gravity, and not a gravitized quantum mechanics like Roger Penrose believes in, then it would seem that this framework of quantum mechanics ought to encompass everything that happens, right? Which would mean that once you know the quantum state of a physical system, then at least probabilistically you have determined its future, right? And then the only place to hide something that is not mechanistic, that does not look like the unfolding of some computation, albeit a quantum computation, would be somehow in our lack of knowledge of the initial conditions, right? I mean, we could talk about, what are the other potential loopholes or the other potential places to hide something non-computational, right? Some people think that, if you had a continuum, if you had an infinite dimensional state space, then, but even if you did, you could say, okay, maybe that lets you do something that was uncomputable in the Turing sense, but it would still be mechanistic in some broader sense, or as long as it's governed by any equation at all. Right. And furthermore, what we know about quantum gravity strongly suggests that that's not true. Right. It suggests that actually there's a limit to the number of dimensions of state space that you can have in any physical system of bounded size. Basically, because if you try to stuff too many bits into too small of a space, then you exceed what's called the Schwarzschild bound, which means that your system just collapses to form a black hole. Okay, so it seems like we do only have, finite dimensions to play with. We can only store a finite number of bits within a bounded physical system. And so, in which case nature would be computational in a fairly strong sense. But even if it wasn't, it seems like it's still going to be mechanistic, unless you have something that is just sort of doesn't fit into the paradigm of modern physics at all, right? And where could you even put that? I mean, as far as I can tell, it seems like either in the initial conditions or nowhere. But, maybe I'm missing something.
Every answer you give me, so many worlds to start exploring. How am I going to do this? Okay, one thing I wanted to just check on, I guess if I can summarize the stance, is even if we have a computer that's powerful enough, hypothetically, and let's say we even know the starting points, it's like the starting condition, the initial conditions of the universe, even then we wouldn't be able to predict because there's a probabilistic nature to the universe that maybe it's uncertain or maybe it's random.
Yeah. Okay. But so this is a very important point. If there is unpredictability, but it is merely the kind of unpredictability of a roulette wheel, right? Meaning you can calculate the complete probability distribution over all the outcomes. You just don't know which particular outcome is going to be realized in this spin of the wheel. Then to me, that seems kind of irrelevant to questions about free will and so forth, right? And many, many, many physicists and philosophers have made some version of this same point, over decades, right? That, so for example, like if I have some radioactive material, right? Quantum mechanics tells me that I can't predict, which specific atom will or won't have decayed, within a certain amount of time, but nevertheless, I know that after this much time has elapsed, this is almost precisely the fraction of atoms that will have decayed, right? And so if humans were unpredictable, but only in that sense, that seems like a really, really weak kind of unpredictability to hang your hat on, to hang your sense of free will on, right? It seems like at the very least, you would want what economists call Knightian uncertainty. Knightian uncertainty, basically it means you don't even have a theory that lets you calculate the probabilities in any well-characterized
Black swan
way.
events.
So you are more radically uncertain than that, right? It's not that you're merely probabilistically uncertain, it's that you don't even have a theory that gives you the probabilities. So quantum mechanics, once you know the initial state, the whole point of quantum mechanics is that it is, at its core, it has an algorithm for calculating the probabilities of all the different outcomes of any measurement that you can make on that system after it's evolved in time, right? So at that level, quantum mechanics would not give you Knightian uncertainty. Right? The place where you might have Knightian uncertainty is if you don't know the initial state. Right. And then, another important thing that quantum mechanics tells us is that you can't, in general, learn the state of a physical system without making a measurement that could disturb that system. Right. And then the state is different from what it would have been if you hadn't measured. And so you could hope for Knightian uncertainty that just comes from the unknowability of the initial conditions. That conceivably quantum mechanics could give you.
I guess that partially throws the simulation hypothesis out of the window with this particular definition of the universe.
What do you mean throws it out of the window? Like, well, in what way?
I guess the main argument of the simulation hypothesis is if you can completely break down the universe into these mechanistic rules, which we have established, we are not sure. It's an open question at this stage. Then at that point, it's harder to say that there's a strong chance that the world is a simulation, like Nick Bostrom has predicted.
Yeah. So again, here I want to cleanly separate two different questions, right? The first question is nature computational, right? In the sense that everything that it does could be simulated, let's say, by a Turing machine, or by a digital computer. Let's say. The second question is nature actually a simulation, in the sense that someone in some meta universe is doing the simulating? Right. I think these are not only are these two separate questions, but either one of these could be true without the other one being true. Right. Okay. So to say that nature, is computable in the Turing sense, right, is to say nothing to the effect that someone is computing it. Right. It could still just be, computing itself, without having to be run on anything else, right? I mean, you get to all of the usual philosophical problems of, if you believe that the universe had a creator, well, okay, who created the creator? Is there an infinite chain of them? And if you say that the creator doesn't need to be explained, then why not say the same about the universe, right? Being Turing computable is sort of an intrinsic property that a system can either have or not have, right? It doesn't mean that anyone has to be doing the computing, right? Actually, a good analogy here is like when we say the universe, when we say that space-time is curved, like as Einstein does say in general relativity, right? So like the most basic misconception people have is that, well, then there must be some higher dimensional space that the universe is curved in, right? But no, the whole point of Riemann's differential geometry that Einstein used in general relativity is that curvature is also an intrinsic concept. Right? You can have a manifold that is just intrinsically curved in a way that someone living on that manifold can detect by just, making some triangles and seeing that the angles add up to something other than 180 degrees, right, or something like that. And it doesn't imply that there is any higher dimensional world that you are curved in, right? It's just an intrinsic thing. Same thing with being computable. Okay. And conversely, I would say even if nature was uncomputable in the Turing sense, so, let's say there was some magic box that we could find on the beach somewhere that would let us solve a Turing uncomputable problem, like the halting problem, to decide whether some arbitrary Turing machine will ever stop running, right? Okay. I would still say people who want to believe that the universe is a simulation, well, maybe it's a simulation running on some post-Turing hypercomputer, right? Who is to say that whatever godlike meta universe is simulating our universe, that universe should be limited only to Turing machines? Right. I don't know what its laws are, right? Turing machines are an abstraction that was developed in this universe, with intuition that came from our laws of physics. Right. And so I think that once again, you have to separate the sort of empirical question, the question that we can actually learn something, from physics that might bear on its truth or falsehood, right? From, on the other hand, the philosophical or the metaphysical question, just like with consciousness.
I want to take a small digression and talk about your journey. You started venturing into computer science and coding around the age of 11 when you wanted to build video games. And back then you were under the impression that these complicated games and programs require complicated programming languages. And once you learned the first few simple programming languages, you thought there'll be more beyond it. And then at some point, you were surprised to discover the Church-Turing thesis that simple Turing machines or very simple programming languages, the most basic programming languages, including the ones with the word basic in it, are enough for you to create this complexity and these really complicated systems and games. What was it like discovering the magic of universality? Firstly, what attracted you to computer science at such a young age? And then what was it like to pull back the curtain and see what goes on behind the scenes?
Well, as you said, what originally attracted me was wanting to make my own Nintendo games.
Right. Yeah.
Because here were these worlds that, seemed almost boundlessly complicated, right? Or at least they could be made boundlessly complicated, right? And yet, unlike our world, someone fully understood these worlds because someone had made them. But how did they make them, right? How did they, not just make a video or a static picture of what is happening, but how did they say what ought to happen in every possible circumstance, in response to everything that the user could choose to do, right? And so to find out what programming was, right? I like to say for me, it was like learning where babies come from. Right. It was like why didn't anyone tell me this before? Right. Because, it's not a matter of, you have to have some giant factory like the Boeing, 747 factory, right. With all sorts of, incomprehensible machinery to make this game cartridge, right? It's just, you just sit at a desk and you write these lines of code, right? It's, at some level, it is a math problem. Right, it's just a question of finding the right abstractions to express what you mean, right? And but then what I could see was that the video games I was playing, were I mean by today's standards they'd be laughably primitive, but by the standards of the early 1990s, looked very sophisticated. They have graphics, they have some 3D, they have backgrounds, they have music, and the kinds of games that I could make were primitive. And I thought, surely this must be a limitation of the languages that I'm using, right? With a more powerful language, you can make a more powerful thing. And so it was a further revelation to me. I would say that no, actually, when we think about programming languages, there's this very low ceiling of universality, right? So like once you have an instruction set that just includes a few basic ingredients, so you have to be able to read things from memory. You have to, and the memory ought to be large, in principle unbounded, but at any rate, you ought to be able to address a very large memory, many different bits. You ought to be able to read bits, write bits, and make conditional decisions. Say, if this bit is a 0, then I'm going to do this. If it's a 1, then I'm going to do that.
It's a Turing machine. Right?
Yeah.
A simple
So
Turing
basically,
machine.
you need
Yeah.
the kinds of the instruction set that Alan Turing wrote down in the 1930s, or that you would see in the instruction set of any modern microprocessor, right? And once you have those, then all the rest is just a question of, well, first of all, how much memory do you have? How many steps can you do per second, right? So there are these quantitative questions. And of course, we've been on a Moore's law trajectory where, those resources have increased exponentially with time for the past 60 years. And then there are questions about what peripherals do you have access to? Is there a joystick? Is there a screen? How many pixels are on the screen, right? But these are kind of, in some way less interesting, right? They don't touch the internal logic of what the program is doing. Okay, in terms of the internal logic, like once you have Turing machines, then in principle you have everything, right? Then from that point forward, it's all just an engineering question of how much time and memory do you need to do what you want to do. So in some sense, and we see many other examples of this sort of universality. Like you might say, well, once the Sumerians or the Phoenicians, created the first alphabets, they could only express very primitive concepts, and surely to express the much more complicated concepts that Shakespeare or Kant, would later express, they would need way more letters in their alphabet. But of course, that's not the case at all, right? Once you have, a nice set of letters with which to express, some rich set of words, then you have hit a ceiling of universality, right? You can express any concept that could be expressed with any alphabet. Right, and so somewhat the same is true of instruction sets for programming languages. right? And but we didn't really know what that ceiling was until Turing, and others like Church and Post figured it out in the 1930s. I mean, Babbage had and Ada Lovelace had basically had the right answer a century before that, right? But they sort of didn't even have the conceptual vocabulary to even pose the question of, is this really the right answer, right? And how would we know? That's what came in the 1930s.
I vividly remember the day I discovered the power of universality. The first programming language I was taught was this language called Logo.
Yeah, I remember Logo.
Yeah, and I think this was second or third grade. And the classes till that point, they had just taught us simple commands: make the turtle go forward, to the right, and back. And the previous class, we had just been introduced to the concept of loops, so the repeat function. And then this class, the teacher finally showed us that if you use a loop, set any starting conditions, this turtle can create these complicated patterns, symmetrical patterns. And I remember it was like the weight had dropped in the class because everyone just suddenly understood the potential of the programming language. It was like you described it was like a magic power. It was incredible.
That's a beautiful example, because it's like you see these like very simple just straight line programs where you just do one instruction at a time, and then you add just a little bit more. It doesn't even seem like that big of a deal. Some conditionals, some variables, some loops, and then all of a sudden you are deep in the ocean, right? Now the sky is the limit of what you could imagine doing, right? And and so you can even read Babbage and Lovelace in the 1830s trying to make this point to people, and it was just so far ahead of their time that they sort of barely even knew what words to use to express this.
It was like a superpower. You're absolutely right. I took this digression to talk about your journey. Let's continue exploring the power of computation. Let's enter the world of quantum computing. I think it would be helpful if we can just define it first so I can create the context for all the subsequent questions to follow. What is quantum computing?
Yeah, so quantum computing is a proposal for using the laws of quantum mechanics, which, as we discussed, are sort of the basic operating system for physics for now 100 years, pretty much exactly. But they're a proposal for how to use these quantum mechanical laws to build a different kind of computer, one that would exploit nature to do computation in a new and different way. And what's the point of that? Okay, well, the first thing to say is that quantum computers would not change the limits of what is Turing computable. Okay, so anything that is computable by a quantum computer, like any function that a quantum computer could compute, could also be computed by a conventional computer. Okay, but there could be an absolutely tremendous difference in speed. Okay, so and this is really the key. Okay, because the key thing that quantum mechanics says about the world is that to keep track of the state of a physical system, you need to keep track of what's called a wave function, right? And a wave function is sort of a much, much vaster object than we have intuitions for. Okay, it basically it assigns a number, actually a complex number called an amplitude, to every possible configuration that you could see a physical system have when you looked at it. Okay, so let's imagine, for example, that I have 100 atomic nuclei. Okay, and each one can store one bit of information. Okay, so for example, it might store it by spinning, by the direction of its spin about some axis, that it could be either clockwise or counterclockwise. Okay, so in this way, using 100 nuclei, I could store 100 bits of information. And so the number of possibilities for how those bits could be is 2 to the 100 power. Right. Okay, but now what quantum mechanics says is no, that's what you see when you look. but that's just a tiny, tiny, tiny little sort of pinhole, vision, pinhole view of what is really there. Okay, what's really there is one amplitude for every possible configuration of these 100 particles. Okay, so if these can be in a quantum state, or in other words, if these can be the quantum version of bits, what we call qubits, right? Then actually, you need to just to specify the state of these 100 nuclei, you need 2 to the 100 power parameters. Okay, so you need one parameter for every possible sequence of zeros and ones that you could see when you measure all 100 of them. Okay, so you could imagine that nature off to the side somewhere has to store some vast scratch paper, that is just way bigger than anything that we directly see, right? For 100 particles, it's 2 to the 100 numbers. For 1,000 particles, it would be 2 to the 1,000 numbers. Okay, 2 to the 1,000, by the way, is much more than the number of subatomic particles that there are in the whole observable universe, which is only like 10 to the 85 or
Only.
so, only like, less than 2 to the 300 power, right? So nature has to, maintain this enormous scratch paper. And then every time something happens to the particles, nature has to cross off all of those numbers and replace them with new numbers, right? So this is a staggering amount of computational work for nature to be going to keep track of these few measly particles.
Mm-hmm.
And so the original thought that led a few physicists like Richard Feynman and David Deutsch to the idea of a quantum computer 45 years ago was, if nature is handing us this computational lemon, if it is being so hard to simulate on our computers, why don't we make it into lemonade? So why don't we build a computer that itself would have this exponential number of amplitudes? And of course, then they immediately face the question, well, supposing that you built that device, what they called a quantum computer, at the time, this was just a thought experiment, but supposing you built it, what would it be good for? Okay, at the time, they really only knew one answer to that question, which was, well, it would help a lot for simulating quantum mechanics itself. Which, indeed is a major, major practical problem that chemists and physicists have been dealing with for generations, right? Some of the highest power computers in the world, including a supercomputer that we have here in Austin called Stampede. A lot of what they are used for is solving the Schrödinger equation, which is the basic equation of quantum mechanics, which tells you how these amplitudes change over time, right? And the reason why this is so expensive, why we need to throw such powerful computers at it, is this exponentiality, right? And so even with the most powerful computers in the world, the chemists and the physicists and the material scientists have to resort to all sorts of hacks and approximations, right? And and sometimes they can't get an answer that is as accurate as they want. Sometimes they have to actually do the experiment, use nature itself as the computer, right? So the original promise of a quantum computer was that you would have a programmable device that could just simulate any quantum mechanical system, of your choice, and that could do it without this exponential slowdown that comes from the fact that you've got exponentially many of these amplitudes that you need to keep track of. Okay, so that was the idea. Now, quantum computing started to enter the public's consciousness, I would say about 30 years ago. Which was when an extremely famous algorithm was discovered called Shor's algorithm. Okay, and what Shor's algorithm showed for the first time was that there is a practical problem that's got nothing to do with quantum mechanics, and yet where a quantum computer would make a decisive difference in solving it, right? Okay, that problem was factoring huge numbers, right? Finding the prime factors of, let's say, a 5,000-digit number, right? And why do we care about that? If we're not number theorists, why do we care about factoring numbers into primes? Well, it so happens that the encryption that protects most of the modern internet is based on the belief that factoring is hard, okay? Or that a few closely related problems in number theory are hard. That you can quickly recognize the answer. It's easy at least with a computer to check that, yes, these numbers are the prime factors of this number. You can multiply them. You can check that they're prime. But if someone gives you the product, then to factor it into primes, that may take millions of years, even with a supercomputer. Right. So the whole system that we use, called RSA, public key cryptography. It's a beautiful, beautiful protocol that was invented in the 1970s. Okay. But it all depends on the belief that factoring and a few related problems are hard. Right. And so what Shor showed in the 90s was that if someone could build a truly scalable, and fully programmable quantum computer, then that would no longer be the case.
How would a classical computer solve the problem of having a large number n and finding the prime factors? How would a quantum computer do it?
Good. So with a classical computer, the obvious approach would just be to try every possible divisor one by one. You say, does 2 go into it? No. It's odd. All right. Does 3 go in? No. 4? Well, all right. I already tried 2. Does 5 go in? Right. And then you could try all the way up to n. Or if you think about it slightly more, you realize, I only have to try up to the square root of n. Right. Because if there was a divisor greater than the square root of n, then there would have to be a corresponding one that was smaller. Okay. But even then, if I have a number with 1,000 digits, well, its square root has 500 digits, right? So I'm still trying, all numbers up to like 10 to the 500 power. That still takes much longer than the age of the universe. Okay. So, after like a half century of effort, right, mathematicians have devised methods for factoring huge numbers on a classical computer that are somewhat better than that. Okay. The best one that's known, or at least that's publicly known, whether the, NSA or some other intelligence agency knows something better, I couldn't say. Okay. But the best thing that's publicly known is called the number field sieve. And it uses some high-powered math, some ideas involving elliptic curves. Okay. But it still takes time that is exponential. So like naive factoring would take time that's exponential in the number of digits of the number that you want to factor. The number field sieve takes time that is exponential in the cube root of the number of digits. Okay, so it's milder, and that is presumably what intelligence agencies are going to use if they want to break, let's say, RSA encryption with a 1024-bit key. Right. But even the intelligence agencies probably can't do it with, let's say, a 2048-bit key. Right. That seems prohibitive even with the number field sieve. Right. So, so it's because that's the best algorithm that we know that, we can still use these systems. Right. We just set the keys to be large enough that it's prohibitive to break them using these algorithms. And then we hope and pray that no one that no one knows a better algorithm, or no one will be able to find a better algorithm than that.
And no one's been running it for 150 years.
Yeah, exactly. Or or ideally, 10 to the 50th years or whatever, right? So but this is sort of the rickety foundation that the whole security of the modern internet is based on, right? And we always knew that this is based on assumptions that we don't currently know how to prove. Right, like no one knows how to prove that factoring is a hard problem for a class, even just for a classical computer. Right, what Shor showed, dramatically, was that if someone could build a quantum computer, then that specific assumption is not true. Right, there is a fast quantum algorithm for factoring. Okay. And, Shor's algorithm was such a dramatic development. I mean, it was, I would say, one of the, 2 or 3 most dramatic scientific developments of my lifetime, in my personal opinion. I'm 43. Right. Okay. But it was so dramatic that, when people, tried to explain it in the popular press, right? They constantly wanted to round it down to, well, a classical computer is limited to just trying all possibilities one at a time, right? A quantum computer, its advantage is it can try everything in parallel, right? It can just try everything simultaneously because that's what quantum superposition means. Right. And so Shor's algorithm would work by just trying every possible divisor simultaneously, in another parallel universe or something like that. Okay. So on a, first of all, if that were really how it worked, then that's good for way, way more than just this specific problem of factoring numbers, right? That would change, pretty much everything in the world, right? AI, finance, everything, right? And so then, this sort of misconception took root, which has been so hard to dislodge, ever since, that indeed that's what a quantum computer would do. It would just dramatically speed up everything.
This is
right?
the header of your blog that will optimize.
It is, right? But then, secondly, we can point out that, like, if it were that simple, if that were all there is to Shor's algorithm, and just try every divisor in parallel, then why did you need Peter Shor to think of that? Right? It's like, that seems kind of obvious, right? Okay, so now we can get to the real core of the matter, right? Which is, you asked me, how does Shor's algorithm work, right? Well, that takes some time to explain, if you want to be honest about it, right? I teach it to undergrads every year. It takes me 3 or 4 lectures to do, right? But okay, so let me explain first what the difficulty is. Okay, so it's true that with a quantum computer, you can create what we call a superposition over all the possible solutions, even if there's exponentially many of them. That's even an easy thing to do with a quantum computer, right? Usually means you put the same amount of amplitude on every possible solution. The trouble is that for a computer to be useful, at some point you have to look at it. You have to measure it. You have to get an output, right? And the rules of quantum mechanics are very specific about what happens when you make a measurement, right? And what happens is that these amplitudes, these complex numbers that we were talking about before, get converted into probabilities. Right? And there's a specific rule for how that happens called the Born rule, one of the most important rules in physics, and actually the only rule of fundamental physics that mentions probability. Okay? And what it says is that the probability that you'll see some outcome is equal to the square of the absolute value of the amplitude of that outcome. Okay, so basically, the further away your amplitude is from 0, the more likely you are to see that outcome. But now, what this means in particular is that if you just measure an equal superposition over all the answers, not having done anything else, then all you're going to see will be a random answer.
Right.
Completely random, right? And now if you just wanted a random answer,
Random
you could have
generator.
you could have just flipped a coin a bunch of times. You could have saved all the billions of dollars to build this entirely new kind of computer, right? So the only hope of getting any advantage from a quantum computer is to exploit the way that these amplitudes, being complex numbers, work differently from probabilities. Okay. And how do you do that? Well, the key is this sort of fundamental phenomenon of quantum mechanics, which is called interference. Okay. Interference is basically just our word for, the way that amplitudes can add up. Right. So if I have, some outcome, right. So some final state of my computer, right, it has some amplitude. Right. But now if I want to calculate what is its amplitude, right, I may need to calculate it as a sum over many different possibilities. Okay, there might be many different possible paths that the computer could have taken that would reach that outcome in the end, right? Just like in the famous 2-slit experiment. If I shoot a photon at a screen with 2 small slits in it, right? And then I ask, what is the amplitude that the photon will end up at a certain place behind that screen, right? Well, now there could be 2 different contributions. Well, there's one for if the photon went through the top slit, and there's another for if it went through the bottom slit, right? And this was sort of one of the crucial original experiments that convinced people that the world has to be described this way in the first place, right? Because what you find when you do this experiment is that there are certain places where the photon never wants to appear. right? Called the dark spots, right? And yet, if I close off one of the slits, then the photon can appear in those places. So to say that again, by decreasing the number of paths that a photon can take to get somewhere, I can increase the chance that it gets there, right? So this is sort of our big indication that quantum mechanics is not just some detail of particle behavior. It is actually changing the rules of probability themselves. Okay. And the quantum mechanical explanation for what's going on is, well, the particle we have to think in terms of the amplitude for the photon to get to this place. And if it happens, let's say that a photon could get to some spot by one path with a positive amplitude, but by a different path with a negative amplitude, then those two contributions can cancel each other out so that the total amplitude is zero, which means the probability is zero, which means the photon can never get there. Okay. Whereas if I close off one of the slits, well, then now there's only a positive contribution or there's only a negative one, which means, squaring it, I get a positive number, right? And so now the photon can get there. Okay. That's interference. Okay. And so you can think of the goal with any quantum computation, any algorithm for a quantum computer to do a sort of massively scaled up version of that two-slit experiment, right? So with every quantum algorithm, the game that we're playing is we're trying to choreograph a pattern of interference so that for each wrong answer, each answer that we don't want, some contributions to its amplitude are positive, others are negative, they cancel each other out. Whereas for the right answer, we want all the different contributions to its amplitude to reinforce each other. Let's say to be all positive or all negative. If we can arrange that, then when we measure at the end, we'll see the right answer with a large probability. Now, the tricky part is we need to do all of this even though we ourselves don't know in advance which answer is the right one. If we already knew, what would be the point, right? And we have to do all of this fast. Because if we can do all this, but only in the same number of steps that a classical computer would have taken, then again, what's the point, right? We always have to compare against the best classical algorithm, and we want to do all of this faster. Okay, so that's a really, really tall order, right? It's like nature is handing us this hammer that is like weirder than any science fiction writer would have had the imagination to invent. This interference hammer, right? And now our job is to figure out, are there any nails that this hammer can hit, better than the hammer that we already had, right? Like a priori, it could have just been simulating quantum mechanics. That could have been the only application. It was a minor miracle that this was good for anything else. Okay, but in order to develop his algorithm, Shor really had to take advantage of very, very special structure in the factoring problem. And if you wanted me to explain this, first we'd have to say a little bit about number theory, elementary number theory, that factoring can be reduced to a different problem called period finding, right? Finding the period of a periodic sequence, a sequence that eventually repeats, but only after, an enormously long time. Right. And then, you want to find out, like, after how many steps does it repeat, right? Being able to compute any desired element of that sequence. Right. And then, we would talk about how you can create a superposition over all the different elements of the sequence. Okay. But now you don't just measure that superposition, having created it, right? If you did, you would just see a random element in the sequence, which you could have gotten without a quantum computer just as well. Okay, what you do is something different. You do something called the quantum Fourier transform. Okay, and this is a transformation of the amplitudes, of the list of amplitudes that corresponding to this sequence, right? That the Fourier transform is one of the most basic operations in math and engineering, right? And basically, what it's used for is for sort of extracting periodicity information, right? So it's a linear transformation that, as engineers would say, converts from the time domain to the frequency domain. So it converts from sort of a sum of different periodic signals to information about what are the periods, being added together. And so you sort of do a version of the Fourier transform, but on this vector of amplitudes. And, of course, you need to know, well, how do you do that? So, this is all the technical work that Shor did. He had to show how you not only do that, but do it efficiently with a small number of operations. And then you make a measurement. And then what Shor further showed was that you get information that may not immediately reveal the period of your periodic sequence, but it's really, really useful for that. And if you just repeat a few times, then with very high probability, you will have enough information to determine the period of your periodic sequence. And then from that, again, using classical number theory that's got nothing to do with quantum mechanics, from that, you can then find the prime factors of a huge number. Okay, so the important point is this is way more subtle than just trying every possible divisor in parallel, right? This is really exploiting interference together with very, very special structure of this specific problem, factoring numbers, okay, in a way that was not at all obvious, right? That, the idea of a quantum computer was around for more than a decade before anyone was able to think of this.
What a fascinating breakthrough. And firstly, I must say, I know it's not easy to condense collapse.
It's not. I've been trying for 20 years, and that I've sort of condensed it down to like 10 or 15 minutes, and I can't do shorter than that.
Oh, I think you aced it this time. I'm happy that I'm the recipient of your final collapse version. I think this was the most perfect explanation of Shor's algorithm that I've come across. We've been flirting around computation complexity as well. We spoke about how much time it takes, exponential time, polynomial time. So let's start introducing that topic as well. Let's define it first. What is computational complexity theory?
So computational complexity is the subfield of computer science that studies sort of the intrinsic resources that you need to solve computational problems. Okay. So by resources, we mean things like the amount of time, the amount of memory. Okay. We could also study other resources like parallelism, right? Number of parallel processors, or randomness, a number of random bits, or quantum computational resources, right? Or many other things besides. But for simplicity, you can think of time and space. Okay. So if you like, we are taking the original questions that Alan Turing and his friends thought about in the 1930s, which were, which problems are computable and which are not, right? Which problems have a Turing machine to solve them and which ones don't, right? And now we're saying, actually, that very often that's not the most relevant question, right? Often, the problems that we really, really care about the most, it's clear that they are computable, right? Like there is a trivial algorithm that just enumerates every possible solution and checks them all one by one. The problem is merely that solution would, on any reasonable sized input, is going to take longer than the age of the universe.
Merely the problem.
Right. The problem is merely that, right? There is a Turing machine. It just might not halt in less than astronomical time, right? And so now, and this became increasingly clear to people in the 50s and 60s as they started building the first actual digital computers and actually using them to do things that, yes, the problems we want to solve are computable, but the algorithms that we have take ridiculously large amounts of time, right? And so now we need to zoom in further with our computational microscope. We have to say, well, within the computable problems, which problems are efficiently solvable and which are not, right? And when we say efficient, you might wonder what that means, right? Like, are we asking, is there a program that takes 10 seconds, or does any program have to take 20 seconds, right? Well, that's a pretty nitty-gritty question, right? That might depend not just on the problem itself, but also on, how fast is your computer, right? Of course, computers have gotten millions of times faster since, even just a few decades ago, right? It might depend on which instruction set do we have, right? It might depend on all sorts of things that are let's say, more, engineering questions than mathematical ones, which is not to say they aren't important, but just that, as mathematicians, we're not, we may not be able to answer, is this 10 seconds or 20 seconds, right? So what we do in computational complexity is that we mainly look at scaling behavior. Okay, so the thing that we care about, rather than like the raw number of steps or the number of seconds, is as you go to a larger and larger input, how do the resources scale? Okay, so for example, we're very happy usually if there is linear scaling, right? If which would mean when your input gets twice as large, then you need twice as much time, twice as much memory, right? That's a very reasonable way to scale. Okay, if you have quadratic scaling, which means you use a number of steps that grows like the size of the input squared, that would say you double the length of the input. So like double the, either the number of records that need to be sorted, or double the number of cities in the map that you're searching for a shortest path, or something like that. And that would say that now the running time of your algorithm increases by a factor of 4. Again, we're reasonably happy with that. We could, if something is quadratic, we could still hope to get it down to linear, right? But these are kinds of scaling that we can deal with, right? What we really don't want to see is exponential scaling, right? Exponential scaling would say every time I add one more to the size of my input, then the number of steps that I need doubles. Right, or it goes like 2 to the power of the length of the input. Okay, because if I have exponential scaling, as we have, as far as we know, for let's say the problem of simulating quantum mechanics on a classical computer, to take one example, right? If we have exponential scaling, then already when my input has size 100 or 1,000. It might be just completely infeasible to handle, right? 2 to the, I can handle 100 squared, I can handle 1,000 squared, but I can't, even with the biggest computers in the world today, I probably can't handle 2 to the 100 power, much less 2 to the 1,000 power, right? This gets into the, the sort of hyper astronomical numbers, larger than the scale of the universe numbers. Okay. And so then a key thing that we study in computational complexity is, among all the problems that we would like to solve, which ones inherently require exponential scaling, and for which ones can we get by with only polynomial scaling, meaning, a number of steps or amount of memory that increases only like the size of the input raised to some fixed power.
Let's start exploring, let's start diving deep into these complexity classes, these animals in cages in this complexity zoo, of which you are the zookeeper. I'm coming up to the first cage and I see this animal called the P complexity class.
Yes.
What is the P class?
Okay, so P stands for polynomial time, and it is the class of all the problems, technically all the decision problems with yes or no answers, okay, that are solvable by some algorithm running on a digital deterministic computer, like that one, or like the ones we all have in our pockets, in polynomial time, by which we mean, the algorithm has to get the right answer for every possible input. Okay, so it always has to work, and it has to halt after a number of steps that grows only like the input size raised to some fixed power. So this is sort of our rough and ready approximation to what set of problems are efficiently solvable by a standard digital computer. Okay. Now it's not a perfect a representation of that, because, for example, if we said n to the 1 million power, right? Well, formally that's a polynomial, but in practice that, you would never want to deal with that, right? So what justifies this definition in practice, the reason why people adopted it starting in the 1960s, was that it turns out that most of the time when there is a polynomial time algorithm to solve some problem, then the degree of the polynomial is quite small. or can be made small. Right.
It's bounded.
So usually when we see problems in P, there is an n squared algorithm, maybe an n cubed algorithm, and only rarely is it worse than that. Right. But even when someone discovers that a problem is in P by finding an n to the 10 algorithm, let's say, very, very often, if they put enough effort into it, they can make it n to the 5. And then they can make that into the 4 and so forth. It's sort of like, you're at least within striking distance of, like I like to say, like if you're Odysseus, you've won the Trojan War, right? Now you just have to find your way home.
Right.
Right.
Okay.
So examples of problems in P, right? P actually includes most of what we do with our computers on a day-to-day basis. Okay, so pretty much every basic arithmetic operation is going to be, correspond to some problem that's in P. Multiplication, division, also, greatest common divisor, reducing a fraction to lowest terms, also finding the shortest path, in a graph.
This is Dijkstra's algorithm.
Yeah, exactly. Yeah. So let's say the kind of thing that Google Maps does when you ask it for directions, that corresponds to a problem in P, okay? And then, a bunch of things that are less obvious. Solving systems of linear equations, okay? Even solving systems of linear inequalities. That's called linear programming. Right, that's also in P. Okay, that took people decades to prove, but we in the 1980s we learned that that's true. Determining whether a number is prime or composite turns out to be in P. Okay, and for that was suspected for a long time. It was only proven in 2002 in a breakthrough by Agrawal, Kyle, and Saxena. Kyle and Saxena were undergraduates at IIT Kanpur at the time that they produced this breakthrough. Okay, and notice, I said determining whether a number is prime. You might say, well, didn't we just talk about factoring, right? Well, so what we know to be in P is only to determine is your number prime or composite, right? The algorithms that we know, if the number is composite, they just tell you that. They give you no hint about what are the prime factors. That still seems to be a much, much harder problem, right? So, this is a beautiful example of how the boundary between what's in P and what's not in P can be extremely non-obvious, right? Like, determining if a number is prime is in P. Factoring a number, well, we don't know, but, we base the whole security of the internet on the belief that problem is not in P. So that's P.
Let's walk up to the next cage, which has this beast called NP. What is the NP complexity class?
Good. So NP stands for non-deterministic polynomial time. Okay. I should caution people, it does not mean not polynomial. Okay. It's something much more subtle than that. Okay. So NP is basically the class of, you can think of it as the class of all the problems for which if the answer is yes, then that can be efficiently checked. Okay, so it may be very, very hard to find a solution, but at least once a solution is found, then that solution can be efficiently checked. So formally, the way we define it is, again, it's a class of decision problems, but now we introduce an asymmetry between a yes answer and a no answer. Okay, and we say that if the answer to the decision problem is yes, okay, then there has to be a short witness. Okay, what does a witness, what does short mean? Short means of size that is at most polynomial in the size of in the number of bits of the input, right? And that witness has to be efficiently checkable. So
it can be verified in polynomial time.
Exactly. So there has to be a polynomial time algorithm that for every yes input, will accept when it's given some witness. Whereas for every no input, there is no witness that causes it to accept. So since that's kind of abstract, it'll help to give an example, right? So let's take the problem of factoring. Right. So, I'll just come back to, one of our favorite examples. Right. So Okay, so technically, factoring is a problem, what we call a search problem, right? Like I say, you have to find the prime factors of this number. Okay, but we can easily come up with decision problems related to factoring. Like, for example, does this number have at least 3 prime factors? Does this number have a prime factor ending in a 7? Or something like that. Okay, so imagine we ask a decision problem like that, about some 3,000-digit composite number, right? Now that problem might take an astronomical amount of time to solve. As far as we know, it does using any classical algorithm, right? But if the answer is yes, then there is a short proof that the answer is yes. Okay, what is the short proof? The short proof is just I show you the prime factorization, right? And you can use the fact that primality is in P, so you can check that yes, indeed, these numbers really are prime. And it's easy to check with your computer that yes, they do multiply to the original composite. And so in that way, you would verify the answer to this question. Okay, but there are many, many other examples of NP problems that should be familiar from experience. Okay, one would be, let's say I give you the dimensions of a whole bunch of suitcases, and I ask, can these fit into the trunk of your car?
Okay.
Right. I mean, maybe listeners have had to deal with this problem in real life, as I have when going to the airport, right? Where like the trunk will not close. So then you say, all right, but what if I just take all the suitcases out and then I try packing them in a different way?
This
right?
is a version of the knapsack problem.
Yeah. Or we call it the packing problem.
The packing problem.
Yeah. But or 3-dimensional packing, if you like, right? We could also have 1- and 2-dimensional versions of this. But it may be. If you imagine that there were hundreds of suitcases, right? There might be a combinatorial explosion of different packing strategies that you could try. Nevertheless, in the end, it's very easy to check whether a solution is valid or not. Namely, does the trunk close?
Right.
Or does it not close? Right. Okay. We could also talk about, I show you a graph of thousands of people on Facebook, and I show you who is friends with who else. And I ask, is there a set of 2,000 people who are all friends with each other? Right. This is called the clique problem. Right. And so again, it might take astronomical time to find that 2,000 clique if it exists. But if someone claims that they found it, then they just have to show it to you. And then it's very easy for you to check whether, are these people really all friends with each other or not? Okay, we could talk about Sudoku puzzles or jigsaw puzzles. They have the same character, right? They might be very hard to solve, and yet it is, in any case, it is very easy to check any purported solution. Okay, so it being easy to check a purported solution, that's the defining property that puts a problem into the class NP.
So the problem itself, finding the solution, might take exponential time, but to verify whether a given solution actually works, that might take polynomial time.
That has to take polynomial time in order for the problem to be in NP.
Perfect. You brought up Dijkstra's algorithm, finding the shortest path between 2 points. The traveling salesman problem would be an example of an NP problem, right?
Yeah. So yet another example of an NP problem would be like, I give you a collection of cities. I tell you the distance between each city and each other. Now I ask, is there a tour that visits each city with, let's say, at most 5,000 miles total? Right. Or, at most this many frequent flyer points or whatever it is. Right. Again, if such a route exists, then you just have to exhibit it. It's easy to check. But if you're not given the route, then there might be, a combinatorial explosion of different possible routes that you would need to check.
Well, Amazon Prime and delivery might be very interested in the answer. Okay, so
they are.
They are.
I mean, they're certainly interested in general in combinatorial optimization. Yes.
I'm sure they're listening. So we've already met P.
I mean, if they've taken undergraduate computer science, then they know this stuff.
Of course they have. We know they have.
Yeah.
Okay, so we've met the animal called P. We've met the animal called NP. Yes. A very simple, silly question for you. I'm sure you can define this in 5 seconds. Does P equal NP?
Yeah, well, so that's the question, right? That's one of the greatest unsolved problems in all of math is this, now extremely easy to state question of are P and NP the same? Okay, it is very easy to check just from the definitions that P is a subset of NP, right? P is contained in NP. Like if you can solve a problem yourself, then in particular, you can also check, a solution, okay? But is the converse true? So if there is a fast algorithm to check a solution, then does that mean that there is also a fast algorithm to find a solution? That is the P versus NP question. Or another way of asking the question is, are there cases where brute force search is inherently unavoidable, right? Are there situations where, like, I give you a problem, I give you a puzzle, it is easy to check a solution, and yet there is no way to find the solution other than, enumerating, some exponential number of possible solutions. Right. So in essence, that is what we are asking. Right. And I like to say that, if we were physicists, right, we might have just said, well, obviously, there are some situations where you need brute force search. Let's just declare that to be a law of nature. Right. And
Nobel Prize.
Yeah. We could have given ourselves Nobel Prizes for the discovery of that law. And then if later it turned out that there was some crazy algorithm that made P equals NP, then we could just give ourselves more Nobel Prizes, right? So, because we're mathematicians, we have to call this a conjecture. No, because the truth is no one has, in 50 or 60 years, okay, no one has been able to rule out that there could be polynomial time algorithms to solve all the problems in NP, right? I wouldn't expect that exists, right? It would be, certainly one of the greatest mathematical or scientific surprises ever in the history of humanity, I would say. Okay, but we don't actually have the proof as of yet that brute force search for NP problems is ever inherently required.
I want to linger on what you just spoke about, the implications of P equaling NP. If we are able to find that proof, how does that change science, technology, research? What is the actual implication of proving this? Yeah,
it's a good question. So the easiest implication to understand would be that essentially all of the encryption that we use, for the internet would be broken. Okay, and so that doesn't mean merely the particular systems that would be broken by quantum computers, right? Like RSA or these systems based on factoring, right? Now we mean all possible crypto systems that are based on hard computational problems, right? Which means just about everything, with like some very, very, rare exceptions, like what's called the one-time pad, right? Which is not based on a hard computational problem, but it requires this enormous pre-shared key, right? Or there's another thing called quantum cryptography that would not be broken, but it would require being able to send qubits over the internet, which would require upgrading the whole physical architecture of the internet, okay? Other than that, all the other types of cryptography that we use would be broken. So for example, you could have no cryptocurrencies anymore, okay? Bitcoin would be broken, Ethereum would be broken, right? It's all based on, the belief that various computational problems are hard, which if P equaled NP, you could no longer have that. Because, then solving these problems like, mining, new coins, inverting these hash functions, it would be no harder than it is to check the solutions. But, I think there would also be pretty massive implications for AI, right? So basically what it would mean would be that, there would be a fast algorithm to solve the problem of find the optimal weights for this neural network. Right? Where by optimal weights, I mean the weight that sort of minimize the loss on the training data, right? Like find the setting of parameters for this neural network that does the best, that causes the neural net to do the best possible job at predicting, all the text on the internet or predicting, whatever else is in its training data. Okay. And so, as you may have heard, this right now is a problem that, mind-boggling amounts of computing power are being spent on, right? OpenAI is right now, trying to raise, Sam Altman says, trillions of dollars ultimately to just build bigger and bigger clusters of GPUs, in order to, a large part of it is just to do this problem of training neural nets, finding the optimal setting of weights, right? So this would have massive implications for that. Okay, in fact, I can't resist sharing something with you that 20 years ago, when people were talking about why is P versus NP such an important question, right? They would sometimes say, well, look, just, philosophically, right? If P equal to NP, what that would really mean, would mean that, finding solutions would be not much harder than checking solutions, right? And so, for example, you could ask your computer to find the optimal compression of Wikipedia, right? Find like the best possible way of compressing or, relatedly predicting, all the text that there is on Wikipedia. And now they said plausibly, in order to do that, you would have to, your optimal compression would have to encode many of the secrets of intelligence, of sort of the whole world that had led to all this text, because like the best way to predict something is to actually have a model of the world that led to all this text being written, right? And so plausibly that would be, revolutionary for AI, right? And so like I use this argument in talks, that I gave, like 20 years ago, 15 years ago. I thought it was a super interesting intellectual point. What I didn't imagine was that someone would actually do that, would sort of take it literally and say, you know what, even if P is not equal to NP, let's just build, take some gigantic data centers and let's just do the best we can at building a neural net that predicts, the text on the internet as well as it possibly can, right? But that is what initially OpenAI and now a whole, Anthropic and DeepMind and Meta and a whole bunch of other companies are doing, and that is changing the world in ways that we all see. I mean, so this is an important point about the P versus NP problem, right? Even if P is not equal to NP, that doesn't mean that whenever you encounter an NP problem that's not in P, you have to give up. Right? Maybe there is special structure in this input, or in the kinds of inputs that arise in the real world that makes the problem easier than the worst case, right? And that seems to be exactly what has happened in AI, right? It was hard to predict that in advance. OpenAI had to actually raise the millions of dollars and, build out the data centers and do the experiment. But we now know that, yes, you get these large language models that, can converse with us in ways that I think if you showed it to anyone 10 or 20 years ago, they would have said, yes, this passes the Turing test. Yes, this is true AI, because we've sort of been exposed to it, then, therefore we do still argue about it.
Well, thank you, OpenAI, for the groundbreaking work. I promised you I was going to park the question of consciousness aside. I've taken your comments about the implications of P equaling NP, but I want to see if there are actually implications on consciousness as well. So Jeffrey Jefferson had said in his Lister oration that not until a machine can write a sonnet or compose a concerto because of thoughts and emotions felt, and not by the chance fall of symbols, could we agree that machine equals brain. That is, not only write it, but know that it had written it. No mechanism could feel pleasure at its successes, grief when its valves fuse, be warmed by flattery, be made miserable by its mistakes, be charmed by sex, be angry or depressed when it cannot get what it wants. Is it possible to extrapolate, let's say we prove P equals MP, if a machine can verify whether it's written beautiful art, or it's written beautiful sonnet, or it can recognize beautiful art, or it can recognize an emotion, then it becomes capable of generating good art and good emotion and writing a sonnet. And at that point, according to Jeffrey Jefferson, machine will equal brain.
Yeah. Okay. So there's a few things to unpack here. Okay. The first one is that the P versus NP question is not the same as the question of can a machine be conscious or whatever, right? They're a little bit orthogonal to each other, right? It's not even the question. P versus NP is not even the question of is AI solvable, right? That's again a different question, right? So like P versus NP is a mathematical question, right? It is it is distinguished from these other questions, and that like we may someday be able to answer it, but via a mathematical proof, right? But the trade-off is that always in math you have to formalize your question first, and the formalization may not fully capture what you really meant to ask, right? So P versus NP is asking, if we have a program to quickly verify something, then do we also have a program to quickly find that thing, right? So if P equaled NP, then what that would mean in some sense would be that any form of creativity where we can quickly recognize it via a computer program. Okay, so that would include mathematical creativity, finding the proofs of theorems. Okay, because from the seminal work in mathematical logic of the early 20th century of Bertrand Russell and Hilbert and Gödel and all of those people, like you could say the upshot of what they did is that there are formal languages for writing mathematical proofs, which are so precise that just a computer program can check whether the proof is valid or not, right? And so if P equal to NP, that would mean, for example, that there would be a fast computer program where you could just ask it, is there a formal proof of the Riemann hypothesis or the Goldbach conjecture or whatever is your favorite other, a math problem of at most 1 million symbols long, right? And, and the program would be able to find that proof in time that was, in a number of steps that was just whatever polynomial function of 1 million. Hopefully something pretty small, right? So any sort of creativity that looks like puzzle solving, right? But for sort of artistic or literary creativity, right? What it would mean if P equaled NP would be that the problem of being creative in those fields via a computer program would be reducible to the problem of recognizing creativity in those fields, right? So generation would reduce to verification. So it would say, if you wanted to have a program to generate great literature, then you would only have to write a program to recognize great literature. Yeah. And then the one could be converted into the other. That's what it would say. But, of course, people can argue, is there even a fast program to recognize great literature, right? That's not obvious. Right. I mean, that's a question in itself, right? Maybe Jefferson, who you quoted, would deny even that, right? Would say that the answer even there is no. Okay, but now I wanted to go back to that quote, right? That you shared, because I think he does something that is sort of very common in discussions of AI, right? He says, well, like until a computer program can compose a sonnet, can compose a symphony. Okay, so there's a few things we can say there, right? Well, the first thing we can say is, can you compose a symphony, right? I can't. Right. Yeah, I mean, so like already here, like if this is where the bar is, we're talking about right. We're talking about things that only a tiny fraction of humans can do. Right. So that's the first thing to notice. Right. Now, second thing to notice is that, despite how high that bar is, we now plausibly have AIs that do those things, as in like within the last 5 years, right? We now have LLMs that will write sonnets on demand. Now, are they the quality of Shakespeare? Well, probably not. But, they have, a lot more energy than Shakespeare. They can write a lot more sonnets.
The more prolific, more versatile.
Yeah. No, and actually for just, writing like amusing verse about any given theme, I would say that they're better than I am, right? Not, so again, not better than Shakespeare, not better than the, maybe the very greatest poets, but probably better than me, right? And we now have AI that can do most problem sets, right? Almost anything in the whole undergraduate curriculum, right? Whether it's physics or math or even, the humanities, writing essays, on given themes, right? It's to the point where it is like an almost existential problem for higher education that millions and millions of students are using, these AIs to do their homework for them, to write their term papers, and again, is it, the greatest quality writing? Could it be published in the New Yorker? Probably not. But it's, very, very often it's enough to get passing grades in most, undergraduate classes, even in graduate classes, right? So that's the first thing to say, right? And of course, what it is now is the worst that it will ever be, right? It can, it will only get better from here.
Yeah.
And it went from, sort of struggling with elementary school to sort of, beating most graduate students at graduate school in the space of, let's say, 3 or 4 years. Right. So that's the sort of rate of progress that we are now talking about. And so you have to imagine, well, what if it does get to sort of, beyond the level of Shakespeare, in a blind test, or, beyond the level of the best human mathematicians, as happened in games like chess and Go. Right, where we are now deeply into the era of AI supremacy, right? Where AIs just got better and better until they were competing against the very best humans, and now there's no longer even a contest at all. They're just so much better than the best humans that humans can barely even understand what they're doing in chess or in Go. But then in that quote, Jefferson added these additional clauses to sort of give himself an out, right? He said, well, it has to be because the machine really felt the emotion and not just because of the chance occurrence of symbols. Right. And you see this kind of move over and over and over again. Right. It's at the heart of, for example, Searle's Chinese room. Right. And people just keep inventing new ways of expressing the same thing, that, it has to have semantics and not just syntax, or it has to have intentionality, or, they like it varies what's the exact thing that it has to have, but it always sort of retreats beyond what is empirically testable.
Yeah, the qualia, right? The experience of it.
Has to have qualia, has to have qualia, has to have experience, has to feel the redness of red.
Mary the scientist, right?
Yeah. The symbols have to be grounded, right? And now, the key is that I am not impressed by this kind of discourse if people don't even notice the question of how do we know that we have those things. Right? Like, okay, I feel like, I have qualia, right? I feel like when I say that something is red, it's not just that my neurons are firing in a certain way to make my mouth move to say it's red, but I feel like I have an actual perception of that thing being red, right? But in your case, all I have access to is really what you say, right? And what you do, right? And everything else I have to infer on the basis of that, right? And if I try to look inside of you using an fMRI or whatever, then what I see looks a hell of a lot like a giant mechanism, right? It looks like a whole bunch of neurons that are, firing according to, rules of biochemistry, or, ultimately the laws of physics, which again, as far as anyone knows, are computable laws. Right. And so now I think the burden is firmly on the AI skeptic to articulate what is different in the one case versus the other. Right. So it is not the AI proponent's job. Right. It is the skeptic's job. The skeptic has to say, what is special about carbon-based biological life that makes it have qualia, whereas the silicon-based computer that does the identical thing does not have qualia, right? Like, what is the key separating criterion? I'm not going to say that they're wrong. Maybe they're right. Maybe there is such a criterion. I'm just going to say it is their job to clearly articulate what that criterion is.
A small proof for them.
Yes. Yeah. It's just a very modest ask.
We can delegate it then. You solve the problem.
Yeah.
Not my problem. Professor, I think we can continue talking about these topics for hours. This has been such a fascinating, and you would also agree, an introduction, just an introduction to the topics. And there's so much more to explore, but we have to start wrapping up at some point. Before we move into final questions, I would love it if you can tell me what masterpiece I've built with the Lego. What do you
What
think?
masterpiece have you built? Oh gosh. Well, I see, a letter L, but I also see some kind of fortress of some kind. Well, it's a fortress, but it's not an impervious one because an attacker could go around this way.
Right.
Yeah, I don't know. And again, it looks to me like a red fortress, but maybe that's just my neurons firing in a particular pattern to cause me to say that.
Well, you did verify that it's a masterpiece, which means if P equals NP, you would be able to generate a masterpiece.
Oh, yes.
Just like this.
I forgot to add, it is an artistic masterpiece.
Yeah, definitely it is. Does look like a fortress, but not a well-planned one. Let's move into some closing questions. What are some books, movies, role models that have strongly inspired you in your life?
Oh, gosh. All right. Well, books. The Mind-Body Problem by Rebecca Goldstein, is an amazing novel that sort of asks all these philosophical questions that are very close to my heart. And it was an honor to back when I lived in Boston to get to know Rebecca, right? And actually also her husband, Steven Pinker, who has also written amazing books that I could strongly recommend. How the Mind Works, The Blank Slate. In Computational Complexity, the textbook by Papadimitriou was revelatory for me. There's another one called Gems of Theoretical Computer Science that I really love. For people who want the basics of quantum mechanics, Richard Feynman has this wonderful popular book called QED. Leonard Susskind has a really nice book called The Theoretical Minimum. Quantum mechanics has been one of the worst popularized areas of science, right? There's just so many bad popularizations, but these are two of the good ones. Sean Carroll has a really, really nice book called Something Deeply Hidden. So those are those would be some great books that would cover some of the things that we talked about. In terms of movies, I think, some of my all-time favorites would be Real Genius from the 1980s with Val Kilmer, who just unfortunately passed away recently. That's a classic. And I'm a sucker for musicals. The Sound of Music, Fiddler on the Roof. But we could spend a long time listing movies that are good. But in terms of people who are role models, I actually some of the ones I mentioned, Sean Carroll, Steven Pinker, Rebecca Goldstein, Leonard Susskind, they're all role models. But when I was a kid, reading Isaac Asimov, reading Carl Sagan, I really aspired to be able to write like they did, or even like as 1% of what they did. Of course, Feynman and Turing, who both of whom we talked about. I could give many other role models from my own life, but they might not be people who listeners would know.
I think this is a great list already. You spoke about aspirations, so let's move into the next question. What would you like your legacy to be? How do you want to be remembered?
Oh my gosh. I don't think it's that productive to think about that question, right? Because it's like if you spend your time thinking about, what will this do for my legacy, right? Then you're less likely to do the actual things that would make that question worth answering, right? I feel like that's the kind of question that almost on principle one should leave to other people.
Well, I am other people. I can answer it for you. I think your work in quantum computing, computation, complexity is already monumental. I'm glad you picked up your brother's babysitter's book on calculus. and because you were interested to find out what dx by dy meant, I think the butterfly effect of that one decision is already monumental.
I mean, I would maybe I'll say this: I would like my legacy to be more than the various arguments I've had in the comment section of my blog.
Yeah, I think that's a rich legacy. Definitely check out the blog and read the comments. I think it is work of art. Final question, the easiest one. I'm sure you can nail this in 5 seconds. What is the meaning of life, Scott Aaronson?
Yeah, I think people who look to science for the meaning of life are bound to be disappointed, right? That's one of the great lessons of the whole scientific revolution, right? That the more we look, the more we find more, intricate, beautiful, elaborate, but mechanisms, right? And we don't really find a guiding purpose, or at least one that seems to care about us. Certainly, we don't find a guiding purpose that cares about us enough to prevent, the worst atrocities, right? There seems to be no limit to, how horrible are the things that humans can do to each other, right? For me, so I think that meaning is a thing that we have to find, right? The universe is not going to give it to us. We have to find it. And for me, what makes life meaningful is, first of all, discovering new things. Second of all, friends, family, our connections to other people, love for other people. And then thirdly, trying to make the world a better place, trying to remedy some of the injustices in the world and the unnecessary suffering that there is.
I can get behind that meaning.
All right.
Professor, if people wish to find out more about you, about your work, read your blog, what is the best way to find you or your work?
Well, I'm not that hard to find. You can go to scottaaronson.com. That's my homepage. scottaaronson.com/blog. That's my blog. I've got a bunch of lecture notes, for my theoretical computer science and quantum computing courses, and those are free on my homepage. I've got a bunch of popular articles that I've written, and I've got a bunch of talks and podcasts, like this one, and interviews that I've done that are up on YouTube.
Many ways to find you. Professor,
and I have a book, Quantum Computing Since Democritus. I almost forgot.
A fantastic book. I highly recommend it. Professor, thank you so much. It has been an honor and a privilege for me.
Well, thank you. It was great to be on this program.